Thank you so much, Seth, for the great introduction. Well, so today I will just briefly explain what we have been done in the past several years. So the topic of the presentation today is tentacle-like continuum robots for minimally invasive surgeries. So actually, when we talk about robot, our first impression might be this giant industrial robot arm, and put in the assembly line to perform different tasks. So these industrial robots are very, very precise, and they can be used to handle different heavy load tasks, for example, welding and lifting some objects. But as you can imagine, so this industrial robot is very dangerous, right? Because they have been operated inside the protective cage. So working along this industrial robot can be very stressful and even dangerous. So in some scenarios, we hope that the robot and human beings can have some safe interaction, just like this. Right, so Baymax is holding hero. So in medical, in robotics field, there are two fundamental approaches to enable safe human-robot interaction. The first approach is called interactive safety. Basically, the different control algorithm or contact force detection algorithm or path planning algorithm can be developed such that the robot can behave safely. For example, when the robot is in contact with a human, and we can detect this contact. So this is called interactive safety. The second approach is called the intrinsic safety. So this is a support board developed by a Japanese company. So different from the conventional robot, this robot is fabricated with some soft materials such that they can be safely interact with other people to keep them stay mentally engaged. So continuum robot can be considered as second group from the materials perspective. So different continuum robots have been developed in the past probably 10 to 20 years. And here you can see a continuum robot that can be used for search and rescue. And this is a continuum robot that can be used for grasping and also even used to twist a screw. And this is a continuum parallel robot, and this is a continuum robot for the endoscopic procedures. So different from the conventional robot that is controlled by the joint. But the motion of the continuum robot are generated by continuous deformed robot itself, because the robot are fabricated with some continuous deformed materials like the silicone or nitinol tubes, nitinol materials. So what I'm particularly interested in using continuum robot is in the medical field. So the main motivation is the ongoing trend to make the procedure less invasive. So here I collect some images from the internet show the scar after procedure. And I want to show you how robot can change the whole story by using different by using the novel techniques. So here is the open brain surgery, and as you can see, this scar is around 10 to 15 inches. But now we can perform the same procedure using a ROSA robot, such that we can enter into the brain from a minimally invasive approach. And here, this is another probably 15 to 20 inches scar after the open abdomen procedure. But now we can use the Da Vinci robot to enter into the abdomen to perform some procedures from the natural opening. So nowadays, we are not only care about whether the patient can live, but also care how the patient feel about themselves. So I'm particularly interested in using continuum robot in medical field. So in our lab, we develop different types of continuum robot. And here is a concentric tube robot, which Seth just mentioned. And the second one is catheter. And here is a catheter manipulated into the left atrium for the ablation. And the third one is soft robot. And we also developed some non-continuum robot like the MR-guided brachytherapy and injection needle and also robot-assisted HIFU. So today I will just focus on how to use continuum robot to save the patient's lives. So the first continuum robot I want to introduce is MRI-compatible concentric tube robot. So here are my clinical collaborators. So what is a concentric tube robot? So basically, concentric tube robot is a group of tubes that are nested together. So these tubes are pre-shaped at different configuration, and each tube can be linearly translated and also axially rotated. So due to this tube interaction, we can create a very complex workspace compared to a straight tube. So let's assume if we have a linear tube, the only workspace is just a straight line. But because this tube is pre-shaped and it is super elastic, we can create a much larger workspace. If we can add some gripper at the end effector, we can use to grasp on tissue, or if we can integrate a laser fiber, then we can use it to perform the laser ablation. So what I'm doing in concentric tube robot is to use it for the intracerebral hemorrhage. So intracerebral hemorrhage is a major healthcare challenge. So it occurs when the blood leaks from the ruptured vessel and then accumulates inside the brain. And this blood will compress the normal health tissue to cause some complications. So it is a very common disease. Around 1 in 50 people will have ICH in their lifetime. So I think here we have more than 50 people. So someone will have ICH in their lifetime, not you. Okay. So around 40% mortality rate in the first 30 days. It's very, very deadly disease. So for the conventional approach for the ICH is very invasive. So basically, the surgeon, well, it's a little bit bloody, so you couldn't get used to just close the eyes. Okay, so it's very invasive. We literally need to remove part of the skull and then take the blood tissue out. As you can see, because of the invasiveness, not all the patients are qualified for this open brain surgery. So neuroendoscope is an ongoing trend to treat the intracerebral hemorrhage, but there are two limitations. First of all, the conventional endoscope is very big. So as you can see, this brain part has a diameter of around 30 millimeters. Just imagine we insert an endoscope that has a similar dimension of a finger. Very invasive. And the second approach is the lacks of dexterity. Because a conventional endoscope is a straight device, if we want to use this endoscope to reach the boundary of this blood clot, what we have to do is we need to tilt this endoscope around this entry point. Because this tilting motion, so this will cause a cone destruction, because this endoscope will compress the surrounding tissue. So if we can evacuate the blood clot from a very minimally invasive approach, we can probably save this patient. So here is our approach. Let's assume that we have an outer tube. This outer tube is straight tube, and it has a diameter of around 1.5 millimeter. And then we have inner tube, and this inner tube is a super elastic one. It's fabricated with 19 materials. If we retract this inner tube, it will become straight one, and then we can insert into the brain. But once we deploy it, because this inner tube is super elastic, it can return to its home initial shape. So this inner tube can cover the entire blood clot. So if we can properly design the inner tube curvature, arc length, and also the insertion orientation, we can make sure that the workspace of the end of the inner tube can cover the entire blood clot. So this is the whole idea. It's very simple. Based on this idea, we build a robot. And as you can see, so we use this red gelatin to represent the blood clot, and we use this transparent gelatin to represent the normal health tissue. So we can say we take all the blood clot out. But from this video, we found out we need to have the image feedback, right? Because in the benchtop test, we cut the brain model into half. But in the real experiment, we want to see how much we have already evacuated. Where is the inner tube with respect to the boundary of the blood clot? So we consider two different types of imaging modalities. The first one is CT, and the second one is MRI. So using MRI can bring some advantage. For example, we can see this tiny blood clot inside the brain. It provides high-resolution imaging feedback. And secondly, there is no radiation to both patients and also the clinicians. So to design a robot that can be operated inside the MRI is quite challenging because the MRI has strong magnetic field. So any device fabricated with ferromagnetic material like the steel can be very dangerous. And also all the conventional DC motors, whether it's brushless DC or permanent DC motor, we cannot use that inside scanner because of the imaging quality and also safety constraint. So as we know, for the robot, we typically need to have the robot hardware, which is actuating part. We need to have the sensing part, and also we need to have the control modeling part. So next, I want to discuss all these several components one by one. First of all is robot hardware. So this is our MRI safe pneumatic motor. The cool part of this motor is that it's fabricated with plastic material, which means that there's no magnetic force between the motor and also the MRI scanner. And this motor is powered by pneumatic power supply, which means from the working principle point of view, it's electromagnetic decoupled from the scanner. So here you can find some specific sheet of this motor. Once we have this motor, we develop some control method to control the motor position. Here I will just show you the Setpoint Tracking. As you can see that we can achieve sub-millimeter control accuracy for this pneumatic motor. Of course, we also test some bandwidth and also sine wave tracking and also square wave tracking. Both can achieve the desired performance. And once we have this robot hardware, once we have the motor, we can build a robot hardware. So here, this is the very first prototype I developed during my PhD, but now my PhD student, Anthony, he is developing a second prototype. We just tested last weekend. So this robot has 3 degree freedom because the inner tube has insertion and also rotation. Outer tube has insertion, so which means we have 3 active degree freedom. And this robot is mounted on a 2 degree freedom aiming device because this aiming device will provide the pulse of this entry point. So in total, it's 5 degree freedom. And once we have hardware, we want to explore the control. So the control of this robot can be achieved with the basic resolved rate control. I think everybody have already learned that. So to start with this resolved rate control, first of all, we need to identify the desired robot trajectory. And then we apply the inverse of the Jacobian that can map from the task space velocity to the joint space velocity, and then we integrate. We can get the joint space position, and then the most important part is we need to have the kinematic and aerostatic model such that we can map the joint space position to the corresponding robot and end effector space position. So to develop this static or kinematic model, we rely on the Kurzweil rod theory. So it's very lengthy derivation, but here I will just show you some very basic ones. First of all, we need to consider the kinematics, and second, we will also need to consider the mechanics, and lastly, we need to consider the constitutive laws. If we combine all these 6 differential equations together, we can solve a slender rod subject to the slender rod deformation subject to the external force or the internal force. Here is a demo shows that once we apply the force at the tip of this soft rod and also at the body of this continuum arm, how the deformation will become. And once we have the hardware, modeling, and also control method, we can validate it in the benchtop and also in the MR scanner. So next, I want to show you the MR validation we did before. So this is a hardware, and we use pneumatic air hose to power the robot, and we have the optical fiber such that we can track the joint space motion. And we test the MR compatibility and also several different experiments to validate the performance in terms of MR safety. Next, I want to just show you 2 critical experiments. First one is accuracy test. So accuracy test means also we have a target inside the MR image, which is this purple point, and we want to control this robot to hit the target. So here, this black part shows the outer tube image artifact because outer tube is metallic. It has a certain image artifact. As you can see that once when we insert this outer tube, we can see that with real-time image feedback, we can always see the relative position between the target and also the outer tube. This task space feedback can be very critical for us to ensure the safe closed-loop control, and also it enhances the confidence level when the surgeon inserts any device teleoperatively based on the image feedback. So they will feel significant confidence about this procedure. This is accuracy test, and next we want to show the efficiency test. Efficiency test is we want to evaluate how much blood clot we can evacuate during the procedure. Similarly, we use the real-time evacuation monitoring to monitor the whole evacuation outcome. And also, it's surgeon in the loop. Basically, the surgeon can tell how much we have already evacuated and how much we need to continue to evacuate. So this is a basic experiment we performed before. So last week we just performed a more comprehensive experiment. We're still in the process of the data analysis. So our ongoing work includes the robot optimization. This is the most updated robot design. And another ongoing work is the robot path planning. Basically, when we insert the needle, should we avoid some critical structure, for example, the DTI and also the arteries inside the brain. So considering the dexterity of this continuum concentric robot, we can play with a lot of path planning algorithm, and also we can investigate the optimal design of the concentric robot Do we use a 3-tube design or 2-tube design, or whether it's just a planar circular tube design or it's a helical shape design? So this is the ongoing work we're trying to do right now. So this is a constraint tube robot. So next I want to talk about the tendon-driven continuum robot. So here are my collaborators. So tendon-driven robots have been used in a lot of medical devices. One of the most common medical devices is catheter. So they have been used to develop different catheters. For example, intra-cardiac catheter. This is the image I want to show you here. And this one is the guiding catheter. So the deformation of the catheter is very easy. Basically, we have steer knob at the handle, and once we pull it, and this will cause the deflection of this tip. That's it. It's very simple mechanical design, but it's very challenging to control because the catheter has a dimension of around more than 1.4 meter, and the material is plastic, and also 19 wire. It's very challenging to control that. So in my research, we focus on the catheter applications in the atrial fibrillation treatment. Here are some information about the atrial fibrillation. And again, it's a very common disease. 3 to 4 million people are diagnosed every year in the United States. How to treat this disease is first of all, the surgeon or the cardiologist need to make an incision at the femoral vein and then insert the catheter from the vein all the way to the heart. Once the catheter is inside the heart, so the RF ablation will be generated at the tip of this catheter. And this ablation or the thermal energy will kill the cell inside the left atrium chamber such that we can block the irregular electric signal. So this will eventually treat the atrial fibrillation to make the heart beat in the normal rate. Okay, but the conventional treatment for the catheter is suboptimal because it has a recurrence rate of around 30 to 50% of the first trial, which means around 50% they will take probably a second trial or third trial because the recurrence rate is very high. Several reasons contribute to this. One of the primary reasons is that there is a lack of feedback, lack of very effective feedback to tell the cardiologist where the ablation target is with respect to the catheter based on the fluoroscope guidance. And it's also very hard for them to tell whether it's an acute ablation or the permanent ablation. We hope we can create a permanent ablation such that we can effectively block the irregular electrical signal. But sometimes we can only create an acute ablation because of lack of contact force feedback. So MR can provide a better imaging resolution of the heart. So, but still, this imaging quality is still not very good. What I'm trying to do is, can we increase the imaging quality of the heart such that we can achieve better feedback? So as we know, imaging quality and also the coil distance has this reverse relationship. So here you can see different imaging coils inside the scanner. We have head coil, chest coil, abdominal coil, and also leg coil. So the coil displacement, the distance between coil to the target and also normalized signal to noise ratio has this reverse relationship. If we can place a coil very close to the target, we can get the highest imaging quality. The question becomes, can we bring the imaging coil into the heart? So having this basic motivation, we try to develop an intra-cardiac imaging catheter. So the design requirements include, first of all, this catheter can be folded for the manipulation, and it can be used or it can be deployed to cover a large workspace within the heart. Because basically inside the heart, we have pretty large catheter, or we have large space. We want to deploy that so that we can image a large field of view. So we got the idea from umbrella, right? Once we fold it, we can put it in the bag. But once we open it, we can cover the whole body. So having this basic working principle, we build the first tendon-driven imaging catheter. And this is the first prototype, and the second prototype looks like this. So once we have this hardware, we test in the animal trials in Hopkins. And so these are the experiment setup. And we test in both ex vivo and also in vivo tissues. And here is the result. As we can see, with this intracardiac imaging catheter, we can achieve more than 5 times the signal to noise improvement, and it achieves much faster imaging compared to the regular body coils. Once we have this imaging catheter, what we can achieve the high resolution image feedback. So with this high resolution image feedback, we can develop the intraoperative imaging interface such that we can monitor and also plan the procedure. So here, this is the left atrial model, and this red circle indicates the desired circular ablation zone, and this blue rod is the catheter. So the catheter shape during the procedure can be obtained with a technique called 3D tracking. So we can achieve faster positioning and also high bandwidth tracking during the procedure. So once this catheter is placed close to the target, we can click the button and say that, okay, we have already ablated this region. And with this intraoperative image feedback, we can already tell how much we have already evacuated and what's the rest we need to how much we have already ablated and what's the rest we need to continue to ablate. So this will tell the cardiologist about the completeness of the whole procedure. So again, so there will be some mathematical model in this. For example, the virtual fixer, for example, when the catheter is inside the heart, so when you constrain this motion, it still penetrates into the tissue, cause perforation. So here, I want to just show you, with this interface, what kind of outcome we can get. So to evaluate this outcome, we want to perform several tests. First is accuracy. So we want to show, with this interface, what's the accuracy improvement we can achieve. And the next is sufficiency of lesion. Basically, we want to characterize how much we have already ablated versus we haven't ablated, and also average procedure time. The last is safety. Safety is the depth of the catheter that exceeds of the tissue model, and also number of tip deviation and also average time. So we invited 10 different subjects to perform the procedure without interface and with the interface. And we can see that with the interface, we achieve significant improvement in all the 6 performance index compared to the one without interface. So on average, subjects demonstrate around 30% improvement in terms of accuracy, efficiency, and safety. So this indicates the significant potential for the clinical use of our imaging catheter plus the navigation interface developed based on this imaging catheter, and also the modeling, such as the catheter modeling plus the virtual fixer modeling. Next, I want to tell you another tendon-driven device inside the tissue. Catheter is the device that is inside the chamber. The chamber is hollow. But now, can we deploy a device that can be deflect inside muscle or inside tissue? Here is our application. We try to use it for the brachytherapy. And this is a clinical background of the gynecological cancer. So to treat this cancer, the surgeon will need to use brachytherapy. So basic idea is we insert this straight stylet into the tissue and then remove stylet, because outside the stylet we have the hollow catheter or hollow tube. Then we deploy the RF seed into this tube or deploy the radiation seed into the tube. And then this radiation will kill the tumor cell. As you can see, the most important part for the brachytherapy is how can we accurately deploy this radiation seed into the patient, right? If we can deploy it at the desired location, then we can kill the tumor. But if not, we probably will kill the normal healthy tissue. So to track the device inside tissue, we use the active tracking technique. Basically, we mount some very tiny tracking coil onto the stylet. It's quite similar to the EM tracker, but the EM tracker is, we need to have the field generator bring into the scanner, but we use RF tracking. So RF tracking is that we can couple to the MR scanner, wireless or wired. So with this tracking technique, you can see its corresponding location inside the MR imaging. And then we get this signal quality, signal of this coil project onto 3 axes, for example, X, Y, Z, and we can get the peak around each axis. So this peak indicates the location of one of the tracking coil in X direction, Y direction, and also Z direction. So once we have this tracking technique, we can create the device in real time, and we test it in the turkey. Here is the needle insertion inside the turkey, and we can see the corresponding location of the stylet in real time. We thought it was great. Then we test in the human trials. We did test that, and we tested in several different human trials. And we found several problems. First of all, so let's analyze this figure. So this cross indicates starting point, and this star indicates target. As you can see here, this is a start and this target. We have a significant error between the starting point and also target. And second, so because we miss the target, the surgeon will need to insert, retract multiple times in order to hopefully, due to some tissue needle interaction, we can hit the target. But so that's the reason we can see this the long trajectory insert going back and forth. So these are the two fundamental problems we found in the human trials. The primary reason is because it lacks the dexterity. Because consider this straight tube, it can only be inserted, right? We are hoping that the target is on the trajectory of this needle, but because tissue deformation and also needle deflection inside the tissue, so there will always be some uncertainties. So that's the reason we couldn't hit the target in a very efficient and also acceptable manner. So to increase the dexterity, we create tendon-driven deflectable styler. It's very easy to build this hardware. We just make some cutout on the tube, and then we use a 19-node tendon wire soldered here. And once we put in this 19-node wire, it can deflect. So this is a deflection of this styler. So once we have this hardware, we can build this model similar. We use rigid frame transformation. We can find the corresponding tendon wire displacement caused to the curvature of this deflector region. And we found this. We tested this device in the benchtop environment. We found that there was a huge error. The error is because this tendon wire not only contributed to the styler deformation, but also contributed to the tendon wire elongation. So this is very important. Nobody considered that before, because previously we just want to make sure this tendon-driven deflection, tendon-driven mechanism. We're hoping that this device is soft, and but in our application, we need to penetrate into the muscle, or penetrate into the tissue. We are hoping. So this deflectable styler is very rigid, so which means that this tendon wire elongation, we have to consider that. So based on this motivation, my student Anthony, he developed an energy-based static model. So in this new model here, this is a tendon wire contributed to the styler deformation, and also this portion is tendon elongation. So with this comprehensive model, we validate experimentally, and we can see that without consideration of the tendon elongation, this is the bending angle, but with the consideration of the elongation, it can match to the experimental data very accurately. Then we tested with ex vivo tissue and with EM tracker. We can find that the overall targeting accuracy is around 2 millimeters, which is significantly better compared to our human trial result. And we tested in the MRI experiment, validated inside the 1.5T scanner, and we found that overall targeting accuracy is around 2.3 millimeters, which is pretty acceptable because MRI imaging resolution typically has a resolution of around 1 millimeter, so we'll achieve 2.3 millimeters. So our ongoing work is to get the IRB approval of this deflectable styler and test in the human trials. So, okay, so the last part is bio-inspired software robot. So these are my clinical collaborators. So software robot, I know some of you have been working on this software robot for several years, but initially it was proposed by Suzumori in 1990s, but it didn't receive too much attention until probably 10, 15 years ago. Dr. Whiteside in Harvard, they developed a starfish gripper they can use to grasp the egg in a very safe approach. Since then, software robot has become a very hot topic. A lot of different software robots have been developed. So here are just some examples. So in 2015, so Daniel and also Michael, they published a paper in Nature about the design, fabrication, and control of this software robot. So in the paper, one of the most important questions they try to answer, or they hope our robotics can answer, is how do we design and control these software machines, and how do we use these software machines? Well, this is a very complicated question. So to answer this complicated one, so we start with a very basic software robot. So let's consider this 1 degree freedom soft robot. Here, this is a pneumatic-driven soft robot. Once we pressurize it, it will be bent to one direction. And this is a tendon-driven soft robot. Basic idea is quite similar to the catheter. Once we pull its tendon wire, it will deform. So to fabricate this type of soft robot, it's very easy. We basically rely on the silicone casting method. So we create the soft robot body first and add the base strain limit layer such that we can constrain its motion in one direction. And also this radical strain limit layer such that we can constrain its motion in the radical direction. And then we add an outer layer to protect both strain limit layer, and then we seal both of them. That's a fabricate of this soft robot. So we can fabricate this soft robot probably within 1 or 2 days. Very easy. But to model and to control this soft robot is very challenging. So the conventional approach for the soft robot control, especially for the kinematics, in terms of from the configuration to the task mapping, is derived based on this constant curvature assumption. So with this assumption, we can find there are 2 problems. First of all, is there is a expression singularity, and second, in reality, so some software that are basically not constant curvature, right? Just like the robot you're seeing here, we cannot just use a part of circular to represent this non-constant curvature soft robot. So what we did before is we developed a calibration-based model. This is also so first of all, we find a mapping from the configuring space to the task space. So let's assume that the configuring space variable is a tangent vector, is a tangent angle along any point. Then based on this basic geometry, we can find the position with respect to the arc length can be differentiation can be written as a tangent vector. And so the next is to find the actual space Q, which is a joint input to the configuring space variable theta. Theta is a tangent vector angle. We know that the tangent angle at any point of this soft robot is determined by the input Q and also the location, right? And then we can write this phi s and also gamma s into this polynomial representation. And what we can do is we can get a family of this soft robot shape subject to different input, and then we can put it into a matrix form. With this matrix form, our goal is to solve the coefficient matrix such that we can map the input to the output. So to solve this coefficient matrix, we can just use a chronic product to solve it in a least square approach. So this is a solution. Now, once we know the actual space to the configured space mapping, plus we know the configuring space to the task space mapping, we multiply them together. We can find a mapping from the actual space to the task space. I don't know what happened. There's a weird shift here. Okay, so having this basic modeling, and we test in the real hardware, and we can find out so the model can match to the experimental result very accurately. I really don't know what happened with this one. Okay, so having this forward kinematics model, we can derive the differential kinematics model and also the inverse very easily using a differential chain rule. So I'm not going to cover that in great detail. So next, we want to talk about stiffness modulation. So why we need to do stiffness modulation? So because we can find a soft robot, sometimes it's quite similar to the octopus arms. So it's very soft. It's very hard to hold a heavy object in our experiment. But we know that so the rigid robot is quite similar to the horse leg, right? They're very rigid, very powerful, but they lack the dexterity or they lack the compliance. So we got the inspiration from the animals, and we are thinking whether we can create some robot that is sometimes soft and sometimes rigid. So we found the tail is meaty, which means it's very soft, but sometimes can be very strong. So we try to, based on this kind of inspiration, we try to add a backbone to the soft robot. By modulating the backbone into the soft robot, we can control the stiffness. So with this basic idea, we create the stiffness modulation with backbone. And we make a hollow channel inside the soft robot. And this black line indicates the backbone, which is fabricated with nanometer such that it can be deformed. By inserting this backbone length, we can modulate the overall stiffness of the soft robot. So this is a cross-section area of this soft robot. Here, this is the 19-node backbone insertion, and we create 3 chambers such that we can put the FBG sensor into this soft robot, such that we can monitor its shape. So with this hardware, we need to consider its modeling. Still, we use the cost-spread modeling. But here, it's slightly different because we have the tendon-driven force. So we need to consider the tendon force here. And this is the force we want to integrate into the previous cost-spread model I just described in the constraint tube. So with this tendon force, so we can say it's deformation subject to a given force. So we developed the model and fabricate hardware. Next, we want to test it experimentally. So this is our experiment setup. We use a linear guide rail to pull this tendon wire. Here we have force sensor such that we can measure the joint space force. At the tip, we put a load such that we can provide a constant force. And here, this is the FBG sensor such that we can monitor its shape in real time. So we first evaluate the modeling accuracy, and then we validate the stiffness modulation. So here, I will just show you the stiffness improvement with this backbone. In overall, stiffness is increased up to 350% compared to the one without the stiffness modulation. So this pink color line indicates the model shape, and this dot line indicates the experiment shape. As you can see, our model can match to the experiment result very accurately. So lastly, I want to show you how to use this soft robot in the clinical environment. So we test this soft robot for the pancreatic cancer treatment. So here is some clinical background. So pancreatic, so far it is still one of the most deadly cancer in the world. So 5-year survival rate is less than 10%. So surgical resection of this pancreatic is very invasive. Literally, they need to cut part of the stomach and also pancreatic head and also the bile duct. We need to cut a lot of organs because the pancreatic cancer typically located at this region, a lot of very confined area. So what we are trying to do is to use photodynamic therapy to treat this disease. The whole idea is that the patient first takes some photosensitive drugs, and then these drugs will be accumulated in the cancerous region compared to it will accumulate more in the cancerous region compared to the normal tissue. Then we expose the light to this photosensitized drugs because there will be more photosensitized drugs here. So this photosensitizer will automatically kill the tumor. Problem becomes how can we bring the light to the pancreas in a very dexterous approach. So here is our solution. This is a conventional laparoscopy. And at this laparoscopy, we put a soft robot tip such that this tip can be deformed. And inside this soft robot tip, we have a very tiny micro camera such that we can monitor the shape, monitor we can provide the visual solving. And we have the tendon wire such that we can deform this soft robot, and we have the PDT fiber such that we can emit the light from the tip such that we can kill the cancer. And this is the invasion setup. Once we have this basic idea, we develop the hardware and we experiment validate it. First of all, we validate its accuracy in terms of position accuracy and also the orientation control accuracy. We can find that both accuracy performance can achieve sub-millimeter. Both accuracy can achieve sub-millimeter performance. Then we test in the animal trials, and this blue dot indicates the navigation camera comes from the the navigation camera, and this red dot indicates the photodynamic therapy laser fiber. And as we can see, we can monitor the whole procedure, and we tested in the animal trials. The performance index involved the tumor dimension. So we'll measure tumor before the treatment and also 21 days after treatment. We can see that the tumor dimension has been significantly improved. So in summary, so in this talk, I'll talk about 3 different types of continuum robot. The first is constraint tube robot. Second is tendon-driven robot. Last is soft robot. So yeah, so next I want to acknowledge my collaborators, advisors, and also my students. They did a great job. And finally, I want to make an announcement because I'm new here, so we still need to hire a lot of talented students to work on this cool project. So we are looking for students in robotics, mechatronics, control design. So if you are interested, just let me know. Shoot me an email. I can reply immediately. And, thank you.
We have time for questions. Do we have anybody else?
Mention that like for the MRI, like intracerebral device, like this is one MRI that is the very body, right?
Uh-huh.
That take for internet that's up in the box.
Well, so that's a good question. So because there are several performance index to evaluate safety, first of all is whether this device can generate heat. So far, we didn't see any heating problem. And second is whether this device is biocompatible. So we have some protection mechanism to cover it, to protect it. So far, we believe it's safe, such that it can be deployed into the heart. Good question. Not yet. So basically, so for this MRI-guided trial, so there are not too many groups can perform this procedure in the. I still need to explore, but so far I know Hopkins, Harvard, and Stanford. So these three, they can do that. So that's the reason we build a strong connection with Hopkins. But Emory side, I'm not quite sure about the interventional MRI capability. Probably they can. I just need some time to figure out who can do that. Yeah.
So you're able to model the stiffness as you consider the backbone and as you otherwise modulating the robot. But I know that soft robots in general tend to be compliant. Are you going to be looking at visual feedback in order to make sure that the robot does what it needs to do in some sense? Or were you able to get accurate enough stiffness modulation in order to
So you are asking whether we rely on the visual feedback to get the shape of the soft robot, or? Yes. You are asking whether with this stiffness without visual feedback we can get to the desired position, right? So yeah, so definitely, so this stiffness, because when we insert this this tendon wire, so basically we add 1 more degree freedom. So this will increase the overall kinematics in some direction. So we didn't explain that in a great detail, because let's assume that if we have tendon wire, let's assume we have 1 degree freedom, but now we add a stiffness, basically we have 2 degree freedom. So we add is dexterity. But in some direction, we lack the dexterity. But in some direction, we definitely will increase its workspace. So it depends on the location of your target. Sometimes we probably, without this stiffness modulator, we cannot reach it. But with this stiffness modulator, we can retrieve that. But in some scenarios, we couldn't reach that target point. It really depends on your target. Does that make sense? Thank you.
Any other questions? Yes.
Yes. Uh-huh. Yes. Actually, so this is our ongoing work. So in our simulation, we consider the nerve, consider the DTI, we consider several very critical nerves, like the eye nerve and also blood vessels. So what we are trying to do is we want to avoid these critical structures while we are reaching to this tube. So there will be some optimization work inside this path plane. So we are still working on it right now. Thank you.